Now let us solve some of the examples based on binomial coefficients. Now here is the first question. We have to show that C1 plus 2C2 plus 3C3 plus so on up to n Cn is equal to n into 2 raised to n minus 1. Now here we will see how this question can be solved by two different methods. Let's see the first method. So we have method 1. Now this method is using the properties of binomial coefficients. Alright, so let's call LHS as sum of a general term TR where R varies from 1 to n. So that means this is our term 1, this is our term 2, this is term 3 and so on up to this is term n. Now we observe that if we see every term, that term has the binomial coefficient of the same count as the term number. So if we are having term R, then it will have CR as the binomial coefficient, as well as there will be the multiplier also, that is 1 C1 2 C2. So the multiplier is also same as the term number. So each term is nothing but RCR, which is evident from the LHS, and we have the summation from R equal to 1 to n. Now this further is equal to, using the property we know that RCR can be written as n into n minus 1 CR minus 1. Now here n once again varies from 1 to n. Now in the summation, since the variable of summation is R, so therefore n will be considered as a constant from the perspective of R, so therefore it can be taken outside the summation. So therefore the RHS is n into summation of n minus 1 C R minus 1. R varies from 1 to n. Now here what do we do is we actually write down all the terms in the summation and see what happens. This is equal to n into, when R is 1, the first term will be n minus 1 C0. When R is 2, the second term will be n minus 1 C1 and so on up to the last term will be n minus 1 C n minus 1, that is when R reaches to the last value of n. Now if you observe closely the terms inside this bracket, it is nothing but the sum of all binomial coefficients in some expansion where the degree is n minus 1. So therefore that is equal to n into 2 raised to n minus 1, which is nothing but the RHS. So in this way we prove the required statement. Now let us see how we can prove the same thing by a totally different approach, that is using the calculus method. So let's see the second method, method 2. Now here we will use the differentiation process to prove the required statement. So for this, here we will consider a basic series of 1 plus x whole raised to n. Now we know that this is equal to C0 plus C1x plus C2x square plus so on up to Cn x raised to n. Now what do we do is we differentiate both sides with respect to x. So differentiating both sides with respect to x, we get n into 1 plus x raised to n minus 1. Now this is a standard result in differentiation. So now C0 is a constant, so its derivative will be 0. The derivative of C1x will be C1. Derivative of C2x square will be 2 C2 into x plus the next term would be 3 C3x square and so on up to the last term would be n Cn x raised to n minus 1. Now here if you observe, we have already got the coefficient part as required in the LHS. So you see that our LHS needs exactly the same terms, that is C1 plus 2C2 plus 3C3 and so on up to NCN. So that means we have to somehow just get rid of x, alright. So to do that, what do? Is we simply substitute x equal to 1 in both the sides. So that gives us, on left hand side we will get n into 1 plus 1 gives us 2, so that is 2 raised to n minus 1, and on the right hand side we will get c1 plus 2c2 plus 3c3 and so on up to finally NCN. That is simply because all the powers of x will become 1 only, as x is 1. So this is how it proves the required statement at the end. Now let's move ahead to another question. Now this is also based on the binomial coefficients, but if we compare this with the previous question, we will see that here we have some numbers in the denominator of every term. Alright. So if we recall, it's the process of integration where we get those particular numbers when we integrate the algebraic function in x. So therefore here, instead of differentiation, we will use the process of integration. So let's once again start off with the binomial expansion of 1 plus x raised to n, which we know is equal to c0 plus c1x plus c2x square and so on up to cn x raised to n. Now here let us integrate both sides with respect to x. So integrating both sides with respect to x. Now here, as we know, during the integration the degree increases by 1 and the term also gets divided by that increased degree. Now while integrating, we will integrate it between the two limits 0 to 1. This is equal to, now when you integrate c0, which is a constant, it will become c0 into x plus c1x will change to c1x square upon 2 plus c2x square will change to c2 into x cube upon 3 and so on up to finally we will have cn into x raised to n plus 1 whole upon n plus 1, and this also is integrated from 0 to 1. Now on left hand side, when we evaluate this integration, we first put the upper limit, that is 1. So we have 1 plus 1, in place of x we are putting 1, so that gives us 1 plus 1 2, that is 2 raised to n plus 1 whole upon n plus 1 minus, now we put x equal to the lower limit, which is 0, so that gives us 1 plus 0 is 1 and 1 raised to n plus 1 is once again 1, so which in turn gives us 1 upon n plus 1. Now here on right hand side, when you put x equal to 1, all the terms, or rather all the powers of x will become 1, so therefore we have c0 plus c1 upon 2 plus c2 upon 3 plus so on plus lastly cn upon n plus 1. Now from this, when we subtract the substituted expression of lower limit, which is 0, now we can see that all the terms are including, or they are having x, so that means when you put x as 0, the evaluation of the lower limit will become entirely 0, so therefore there is no need to write anything, and therefore on left hand side we can merge the two terms and finally have 2 raised to n plus 1 minus 1 whole upon n plus 1 is equal to nothing but the required expression, which is the LHS. So that proves the required statement.